Hello, my name is Dragos Stefanescu, and I'd like to thank ChemAxon for the invitation to their user group meeting 2019. I'm a medical computer scientist working for Sanofi Scientific Computing Department in Germany, which is part of research, and it's my pleasure to guide you through this video demonstration of our Similarity graph tool. Please note that all examples shown in this video are based on publicly available Campbell data and for illustration purpose only. This web application was built using Tom Sawyer perspectives, which will be subsequently abbreviated as TSP. Let's get started. First, we do a simple structure search of a Campbell compound. We are using here Marvin.js from ChemAxon to draw load structures. Our TSP web application sends them to our Neo4j graph database for performing substructure searches utilizing the ChemAxon for Neo4j plugin. As a result of this search, we get a star-like graph where the searched compound node is located at the center. Its nearest neighbors in terms of chemical similarities are placed around this center compound node and connected via similarity edges to it. The chemical similarity value is labeled on the respective edge. Clicking on a node displays two things. First, the edge with the highest similarity gets automatically highlighted in red. Second, the property inspector on the left shows all properties of the selected object. In this case, we have the Campbell ID 1834852, we have a calculated molecular weight, calculated A-log P, calculated formal charge, and many others, as well as a Campbell URL. Let's click on that. As you can see, the respective Campbell page has opened for this compound. Let's go back. We would like to display all structures for the compounds on the screen. Here they are. Let's apply two filters that I pre-configured. An A-log P filter that keeps all that are less or equals than 4.334, which is actually the A-log P of the center compound, and another filter that keeps less or equals to a molecular weight of 517. After applying it, you see that the respective nodes and edges got filtered out. Now let's traverse the path along its highest similarity edges. Start with the center node, double click on it, and that gives it its order number 1 because it's the first node of the path we want to traverse. The highest similarity edge is this, double click on that, and now we got the next one marked on our path. Let's keep the filter going and also traverse this edge now. So you can see there are two edges having the same similarity value. And apply the filter also here. Let's do an auto layout to make it a little bit nicer. And we can also toggle between the full graph and just our path. Let's switch the layout to circular, which naturally shows the chemical similarity clusters that we have in our database. Now we like to calculate the shortest path between, let's say, this compound and this one here. And we do that for the visible compounds on the screen. Again, we can also toggle between the non-shortest path and the rest of our graph back and forth. We remove the shortest path for now as we don't need it at the moment. Of course, we can also zoom in and out, move everything around, have a look at the nodes, click each one we like. Let's go back to our start node and let us display all the related projects. Let's do an auto layout and maybe hide the structures. As you can see, we may now need a different way of layouting, and we choose hierarchical layout for that. That looks much nicer. Next, we would also like to display all the scaffolds for that compound. And you can see them here and see which scaffold is shared by which compound on the screen. Again, we can zoom in and out and look at the interesting areas of our graph. As we are currently only interested in hERG-related compounds, we're going to remove this other project here. And do an auto layout. In the next step, we like to enrich our graph with some data that we have in a CSV file. It's hERG activity data. And we specify the file name, the separator, and the decimal delimiter, and join the data from the CSV file by compound ID. So it found actually 3 matching nodes in our graph on the screen. So let's remove the filters and look at another attractive feature, which is the color coding. So let's see first all nodes that have a hERG activity. And they are colored in yellow. So if we click on one of them, we see that this hERG activity properties shows up for these yellow marked nodes. Okay, now we remove that color coding for it. And let's say we're interested in color coding based on more than one property. So I've prepared a color coding rule which says A log P should be less than 3.971 and the hERG activity should be less than 8.06. Let's apply that and see what we get. We can also highlight the first compound that we searched for at the beginning. For that I have prepared this color coding rule, and you see it's the one here. So we now zoom into the graph and think that this could be interesting to look at these nodes, because the ones colored in green fulfill our search criteria for color coding. At this point in time, it's worth mentioning that we can store our graph and also load it afterwards. We could also send it to another user who opens it on his screen within the application and starts working maybe on the same or different branches of the graph. Let's do that. Okay, so the graph was stored. Now let's pretend we were different users, so I will clean that area here. So we start with an empty graph. It's also worth mentioning that the graph that's currently depicted gets automatically saved after a minute of non-use of the application. So it gets saved to the server, so when you go for meetings or for lunch, it will not disappear. So now we open the graph that we stored, pretending to be another person. And there it is. So the other person can, but is not forced to apply the color coding rules. They are automatically loaded with the graph that was sent, and we can save and load color coding rules that we have and share with others. For the compounds we are now actually interested in, we could mark them pressing the control key and right mouse click and send them to other tools, in-house tools like Certara D360 or other in-house tools, and just continue analyzing these maybe interesting compounds. For now, another interesting option is clustering. Let's say we want to cluster all these compounds that are in our graph and cluster them in exactly 5 clusters. For the compound weight, we choose the triangles that we calculated. That's a clustering algorithm provided by Neo4j. So we click on apply, and underneath there's a table view, which we can also sort by the cluster number, and we can see that all our compounds have been automatically assigned according to their triangle count to one of the 5 clusters. So we could use that and export it to Excel and use it for further analysis in different tools. So I'm going to remove the scaffolds because we don't need these any longer for the next example. I'm adding a new compound to the already existing graph. And as you can see, these two graphs are not connected with each other yet. So let's see if we find the shortest path between these two compounds here based on data from the Neo4j database. So we perform load shortest path from database. And let's choose the orthogonal layout for that. And as we can see, there is a shortest path, which we will toggle to so it becomes clearer. Let's do auto layout. And there it is, shortest path from these two compounds is right here. We are now at the end of my video demonstration. In case of any further questions, please do not hesitate to contact me at this email address. Thank you for your attention, and bye-bye.